right, so let's get started. Why doesn't everyone take 10 more seconds to answer this clicker question here? All right, so good. It looks like just about everyone is able to go from the name of an orbital to the state function. That's important, and we're actually going to get a little bit deeper in our clicker questions here, since when you do your problem set, it won't be quite this straightforward that you'll be answering this kind of question, but actually you'll be thinking about how many different orbitals can have certain state functions or certain orbital names. So let's go to a second clicker question here and try one more. So why don't you tell me how many possible orbitals you can have in a single atom that have the following two quantum numbers. So let's say we have n equals 4 and m sub l equaling -2. How many different orbitals can you have that have those two quantum numbers in them? And this should look kind of familiar to some of the problems you may have seen on the problem set if you started it this weekend. So this should be something you can do pretty quickly, so let's take 10 more seconds on that. All right. Okay, looks like we got the majority, which is a good start, but we have some discrepancy on what people are thinking. So let's go through this one. So what we're saying is that we have n equals to 4 and m sub l being equal to -2. If we have n equals 4, what is the highest value of l that we can have? 3. Okay, we can have n4, l3, and then sure, we can have m sub l equal -2 if l equals 3. What's the second value of l that we can have? 2. Okay, so we can have this orbital here. What about l equals 1? Can we have this? No, we can't, because if l equals 1, we cannot have m sub l equal -2, right? Because the magnetic quantum number only goes from -l to positive l here. So that means it's not possible, if we've made these stipulations in the first place, to have a case where l equals 1. So this means we can only have two different values of l. We already know our value of m. So now we're just counting up our orbitals. An orbital is completely described by the 3 quantum numbers. So we end up having 2 orbitals here. All right, so hopefully if you see any other combination of quantum numbers, for example, if it doesn't quickly come to you how many orbitals you have, you can actually try to write out all the possible orbitals, and that should get you started.